In this video, we will go over the axioms Euclid uses for his system of geometry. As we mentioned in the previous video, axioms are statements which are accepted without proof to give us a foundation from which we can prove other things. Euclid divides these into what he calls postulates and common notions. In general, these statements were called first principles by the ancient Greeks, being statements which were impossible to prove and must therefore be assumed to be true. The key difference between the two types is that common notions are things which are self-evident and not particular to geometry, while the postulates are specific to geometry, not necessarily self-evident, and mostly concern the existence of objects. So the postulates start as follows. Let the following be postulated. Postulate 1, to draw a straight line from any point to any point. So the first postulate pertains to one of the tools which we are allowed to use for constructions, which is the straight edge. It says that if we have any two points, A and B, we are allowed to use our straight edge to connect them with a straight line. So you can imagine taking your ruler or whatever you're using for a straight edge, placing it so that it touches points A and B, and then using a pencil to draw a straight line connecting them. Although Euclid does not state it explicitly, we are meant to understand that there is a unique straight line passing through any two distinct points, which we talked about in the previous video. Similarly, if two straight lines have 2 points in common, then they must be the same straight line. This is also equivalent to the assumption which has appeared in various editions of the Elements that two straight lines cannot enclose a space. So if we draw two straight lines, there's no way to make it so that they completely enclose a space. We need at least 3 straight lines for that. Next we have postulate 2, to produce a finite straight line continuously in a straight line. So Euclid is saying here that if we have a finite straight line AB, we can again take our straight edge, place it up against that straight line, and continue to produce it in either direction as far as we want. Note again here that we are assuming that the produced straight line is unique. In other words, there is only one way that we can continue to produce a straight line in a straight line. This also implies that two different straight lines cannot have a line segment in common. We mentioned in the previous video that if we have two different straight lines, at most they can meet at a single point. So postulates 1 and 2 are the only postulates pertaining to the straight edge, which means that the only things we are allowed to do with our straight edge are to draw a straight line connecting 2 points, or to extend an existing straight line. Notably, we are not allowed to measure anything with our straight edge, so sometimes we call it an unmarked straight edge. The use of a marked straight edge would allow many more constructions than would be possible with the unmarked straight edge. Next we have postulate 3, to describe a circle with any center and distance. So this is the compass postulate. This says that we can use our compass to pick a point, and then pick a radius and describe a circle. So the way the compass usually works is that it has one sharp point and then one pencil point. You would place the sharp point where you want the center of your circle, and then the pencil at how far you want the radius, and then you would spin it around in a circle. Note that the word distance in Euclid's postulate is referring to the radius of the circle, the distance from the center to the circumference. Also note that this postulate does not allow us to measure a distance, pick up the compass, and then draw a circle of that radius somewhere else. So there's a tool in GeoGebra for this, this red compass tool here. This tool lets us take a line segment, select that as our radius, and then place that circle anywhere we want. So we are not allowed to do this with our compass in Euclidean geometry. So because of this, we often call it the collapsing compass, meaning that as soon as you pick it up off the paper, it collapses. It doesn't hold that distance. However, we will be proving very early on in the Elements that we can use our tools to construct a copy of a line segment at a point somewhere else, which will essentially allow us to work with a non-collapsing compass. We'll also make the remark here that the first three postulates have postulated the existence of straight lines and circles. So far we know that points exist, we know that straight lines exist, and we know that circles exist. Next we have postulate 4, that all right angles are equal to one another. So this one is a little bit different in that it doesn't give us a construction that we can do. It might seem obvious that all right angles are the same, but remember that all we know about right angles so far is from the definition, which says that they are the angles we get when a straight line stands on another straight line and makes the two angles equal. Nothing that we have assumed so far actually tells us that all right angles everywhere will always be the same. The assumption that all right angles are the same means that we can use them as sort of a standard for measuring other angles. So you'll recall in the definitions we defined an acute angle as an angle smaller than a right angle and an obtuse angle as an angle bigger than a right angle. These definitions wouldn't be very useful if right angles could be different. Having the right angle as a standard for measuring angles was important for Euclid because the ancient Greeks didn't have angle measurements like degrees or radians that we use today to measure angles with. Note that this axiom is equivalent to the assumption that all flat angles are equal, meaning the angle formed by a single straight line. As we will see, this postulate is important for postulate 5. Next we have postulate 5, that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which are the angles less than the two right angles. So this is by far the most interesting of Euclid's axioms. We typically call it the parallel postulate because really this postulate is telling us something about when lines are parallel and when they aren't. So first, let's talk a little bit about what this postulate is actually saying. So suppose we have the straight line AB, and then we make another straight line, CD, and then we have a third straight line that crosses both of those two straight lines. So the two angles that Euclid is talking about are the two angles on the same side, so the angles BGH and GHD here. We can see if we add these up that they sum to less than 180 degrees, so less than two right angles. So what the postulate is claiming is that that means that the two straight lines will eventually meet on that side. And we see that they do over here at point I. So this postulate was often criticized because it really felt like a theorem. In other words, it feels like this is something that we should really be able to prove using the other axioms rather than something that we have to assume. In fact, it seemed that Euclid himself even felt a little bit uneasy about this postulate because he did not use it until proposition 29 of the first book. It seems as though he wanted to do as much as possible before having to use this postulate. Now, many people tried to prove the parallel postulate throughout the years using the other Euclidean axioms, but these proofs were found to be flawed because all of them ended up making assumptions which did not follow from the other axioms. Eventually, in the year 1763, around 2,000 years after the Elements was written, a German mathematician named George Klugel wrote a dissertation in which he examined 28 existing attempted proofs of the parallel postulate, and concluded that it may not be possible to prove at all, and that our certainty of its truth may only be the result of the fact that it seems to align with physical reality. Klugel may have been the first person to express this idea, which is quite remarkable given the amount of time that had passed since the Elements was written. And as it turned out, Klugel was correct. To see why, we will look at the interesting approach taken by the Italian mathematician Girolamo Sacchari, who lived from 1667 to 1733, to attempt to prove the parallel postulate. He started with a straight line segment, AB, and at each endpoint he drew perpendicular segments of the same length, so AC and BD, and he connected the endpoints at the top to form a quadrilateral. In Euclidean geometry, we expect that the angles at the top will also be right angles and that the quadrilateral will therefore be a rectangle. But it is also possible that they are both obtuse angles or that they are both acute angles. Since it was believed that Euclidean geometry describes our physical universe, and therefore it must be the correct geometry, Zachary tried to produce contradictions in the other two cases and thus prove that the right angle case was the only possibility. He called the three possibilities the hypothesis of the right angle, the hypothesis of the obtuse angle, and the hypothesis of the acute angle, respectively. His work was quite shaky, and he failed to produce convincing contradictions in the hypotheses of the obtuse and acute angles, but he unknowingly laid the foundations for what was to come. Mathematicians eventually realized that the hypotheses of the obtuse and acute angles in fact did not produce contradictions. What this means is that each alternative gives us an equally valid system of geometry. These other systems were first investigated by the mathematicians Carl Friedrich Gauss, Nikolai Lobachevsky, and Janos Bolyai. The astonishing conclusion is that Euclid was correct to include the parallel postulate as an axiom all along. Since the other alternatives are equally valid, it is independent of the remaining axioms, and we can choose whichever option is the most convenient. It also raises an interesting question. If there are other valid systems of geometry, how do we know which of them describes our physical universe? It certainly seems that our reality is Euclidean, but our senses can often deceive us. Surprisingly, it turns out that we actually cannot know this. Just as the inhabitant of a two-dimensional universe would have no way of determining the curvature of their universe from within it. What we would need is a fourth-dimensional being looking at our universe from outside and then coming back in to tell us what the curvature was. Unfortunately, this has not happened yet. So, returning to the Zachary quadrilateral, as we now call it, the other options are that the summit angles are acute, which results in what we now call hyperbolic geometry, or they are obtuse, which results in elliptic or spherical geometry. There are several other interesting differences between the different geometries. One is that in Euclidean geometry, the sum of the angles of any triangle is always equal to two right angles, which we will prove in the elements. Whereas in hyperbolic geometry, this sum is less than two right angles, and in elliptic or spherical geometry, it is always greater than two right angles. In fact, in the non-Euclidean geometries, different triangles can have different angle sums, unlike in Euclidean geometry. Another result of all of the attempted proofs of the parallel postulate is that we now know several alternative assumptions which are equivalent to it. By equivalent, we mean that if we assume one of the statements, we can use it to prove the other, and vice versa. The most famous example is Playfair's axiom, named after the Scottish mathematician John Playfair, who lived from 1748 to 1819. Although technically this axiom was known as far back as Proclus in the 5th century AD. It states that given any straight line AB and any point C not on that straight line, there is a unique straight line through C which is parallel to the line AB. So in other words, if we move this straight line through C around, every single one of those lines is going to intersect the line AB except for a single one. This is certainly what we expect in Euclidean geometry. Any deviation at all from that parallel is going to intersect the other line. In hyperbolic geometry, on the other hand, we find that there are infinitely many straight lines through that point which are parallel to the original straight line. This happens because in hyperbolic geometry, the space has curvature, which causes straight lines to diverge from one another. Another equivalent formulation to this postulate is that straight lines which are parallel to the same straight line are also parallel to one another. In other words, being parallel is transitive. If the lines DC and AB are both parallel to the straight line through E at the bottom, then they are also parallel to one another. A couple more interesting equivalents to the parallel postulate are, given any 3 points not in a straight line, there exists a circle passing through them. So we can show an example of this if we have 3 points F, G, H, and they're not all in a straight line. We can construct a circle which passes through all 3 of those points. And the way that we would do that, which I won't go too much into the explanation of here, is we would draw the perpendicular bisectors, and then we would draw a circle with the intersection as the center, and it would pass through those 3 points. And then another one is a rectangle exists. So only in Euclidean geometry do rectangles exist. Non-Euclidean geometries are fairly interesting, but since we are doing the elements, we will be focusing just on Euclidean geometry for this series. So that finishes up the postulates, and we now move on to the common notions. So common notion 1, things which are equal to the same thing are also equal to one another. So remember that the common notions are meant to be self-evident statements, and this one is fairly self-explanatory. This is talking about the transitive property of equality, which says that if A is equal to B and B is equal to C, then A is equal to C. Now, what A, B, and C actually are is fairly irrelevant, although we do need to know something about them in order to know how to determine whether they are equal to one another in the first place. Next, we have common notion 2. If equals be added to equals, then the wholes are equal. This is saying, in other words, if A is equal to B and we add C to both, we get A plus B is equal to B plus C. So adding something to two things that are equal preserves that equality. Common notion 3, if equals be subtracted from equals, then the remainders are equal. So similar to common notion 2, this one is saying that if A equals B, then we have A minus C is equal to B minus C for any C. Next, common notion 4, things which coincide with one another are equal to one another. So this one is fairly interesting. What it is attempting to do is to give us a way of knowing when two geometric figures are equal to one another, or as we would say in modern geometry, when they are congruent. Euclid does this using what is called the principle of superposition, which essentially says that if we take one geometric figure and pick it up and place it on top of another, and if doing so causes the two figures to coincide everywhere, then the two figures are equal. Notably, Euclid didn't really like using this principle and doesn't call on it very often, but because he uses it very early in the elements, a lot of the elements ends up depending on it, making it a very fundamental idea. The principle of superposition is a little bit strange because nowhere else in Euclidean geometry do we really talk about geometric objects moving around. Because of this, there have been a lot of criticisms of this common notion, similar to the parallel postulate. Rather than talking about all of them here, however, we will wait until we reach proposition 4 of the first book, which is the first place that Euclid really makes use of this common notion. One other note here, though, is that since this axiom seems to be particular to geometry, it maybe should have been a postulate instead of a common notion. Finally, we have common notion 5, the whole is greater than the part, which is fairly self-explanatory. So that is all of Euclid's axioms, meaning those are all of the things that we are assuming to build up our system of geometry. However, there are a few other assumptions that Euclid made without explicitly stating them, so we'll talk a little bit about that here. The most significant of these has to do with the intersections of lines. So there are various instances where Euclid assumes that lines will intersect in a certain way, and really we should have a postulate that tells us what will happen in these cases. One way to do this is with the principle of continuity. So one way of expressing this principle is to say, suppose a line belongs entirely to a figure which is divided into two parts. Then if the line has at least one point in common with each part, it must also meet the boundary between the parts. Note here, we are not just talking about straight lines, we are talking about any kind of line. So to show a quick example of what this means, suppose we have this circle that is divided into two semicircles by the line BC. And suppose that we have a line segment that begins in one of the semicircles and ends in the other semicircle. The principle of continuity says that because that line begins in one of the parts and ends in the other, it must at some point intersect the boundary between the two parts. Now, again, this should feel fairly obvious. This is kind of how we expect lines to behave. But again, we really need postulates to tell us how our geometry is going to work. We can never just assume something without explicitly stating it. We can also express this principle using the motion of a point. So if a point moves in a figure which is divided into two parts, and if it belongs at the beginning of the motion to one part and at the end of the motion to the other part, it must during the motion arrive at the boundary between the two parts. So this is similar to what we talked about in the previous video, where we can think of a line as the path that a point takes as it moves through the plane. If we imagine a point D starting in one of our two semicircles, there is no way for it to get over to the other semicircle without at some point crossing that boundary. Another way we can handle the intersections of points and lines is by using the postulate of Dedekind, which is named after the German mathematician Richard Dedekind, who lived from 1831 to 1916. So Dedekind's postulate, and it's a little bit long, but it says if a segment of a straight line AB is divided into two parts so that it has the following three properties. 1. Every point of the segment AB belongs to one of the parts. 2. The extremity A belongs to the first part and B to the second. And 3. Any point whatever of the first part precedes any point whatever of the second part in the order AB of the segment. There exists a point C of the segment AB, which may belong to either one part or the other, such that every point of AB that follows C belongs to the second part in the division originally assumed. So we'll show in GeoGebra exactly what this looks like, but the key thing here is that the postulate is guaranteeing the existence of that point C. So suppose that we have the line segment AB. Now the postulate assumes that we can place all of the points that make up AB into some order, starting with A and ending with B. And what it says is that if we divide this line segment into two smaller segments, essentially there's always a point of division such that all of the points in the first division come before C in that order, and all of the points in the second division come after C. And then, of course, the point C itself belongs to either one division or the other. It's not really important which one. And again, the important thing here is that no matter which way we divide this line segment into two smaller segments, we always get that single point of division somewhere. Now we can use the postulate of Dedekind to prove a similar result about angles, namely that if we divide an angle into two smaller angles, there always exists a single ray which produces that division. And similarly, we can get a result about segments of circles, namely that if we divide the segment of a circle into two smaller segments, we have a single point on the circumference which produces that division. Now, Dedekind's postulate allows us to prove a couple more important results. We won't go through the proofs here, we'll just state the theorems. Theorem 1, if a straight line has one point inside and one point outside a circle, it has 2 points in common with the circle. And theorem 2, if in a given plane a circle has 1 point inside and 1 point outside another circle, the two circles intersect in 2 points. So let's take a look at what these two theorems are saying. The first theorem is saying that if we have a straight line, meaning particularly an infinitely long straight line, and it has one point C inside a circle and another point D outside of a circle, then it intersects that circle in exactly 2 points. And then the second theorem says something similar about when we have two circles. So if we look at the circle AB here, we see that the point B on that circle is inside of the other circle, and then the point E over here is outside of that other circle. So theorem 2 tells us that we will have, again, exactly 2 points of intersection, which are F and G. Of course, the other things that could happen are we could have two circles which don't intersect at all, or we could have two circles that intersect at a single point. And this could happen either with one circle inside of the other like this, or let's move over here. It could also happen with two circles touching on the outside like this. So one more thing to note before we wrap up this video is that it's very important in your system of axioms to have exactly the correct number of axioms. On one hand, you don't want to have too many axioms because this creates a couple of potential problems. One problem is that if you just assume too many things at the beginning, there isn't really much left to prove. And that doesn't really tell us much because we've just assumed everything. The other potential issue is that there could be hidden contradictions if you have too many assumptions. And if you have even a single contradiction in your axioms, that invalidates your entire system. On the other hand, you don't really want to have too few axioms, and that is in some sense what Euclid did, since there are, as we mentioned, a few things that he assumes without explicitly stating. You really want to be very explicit about everything you are assuming, because otherwise people can poke holes in it and say, well, technically you can't prove this unless you assume this thing which you didn't state. It really is a testament to the genius of Euclid, though, that he knew that the parallel postulate needed to be included as an axiom. So that about does it for Euclid's axioms, so in the next video we will finally get into the propositions.